Okay, welcome back. So first, a quick announcement. The homework number 2 will be posted today, and you will have 1 week to do it. For homework 2, there will be part A and part B. And part A will be handled like an assignment. In other words, you put your answers in a document and you upload the document. For part B, I will post a PDF of the questions so that you have time to work on the answers. And then when you are ready, you will take it as a test on e-learning. Okay, so you have 1 week, 1 week to work out the answers, and then you have to take the test by that due date, which is in 1 week. Essentially, it's set up that way because there are some questions which can be automatically graded if it is set up as a test on e-learning. So just stay tuned for the announcement for homework number 2. Okay, so let's look at the UDP protocol, which stands for User Datagram Protocol. The checkpoint question was scary. Okay, why was it scary? Oh, I missed it. Yeah, that was one of the more difficult checkpoints. So some checkpoints are easier, some checkpoints are more difficult. I think this one, the one I just posted, is among the more difficult ones. No more attempt, no, it's a 1 attempt checkpoint. Yeah, because if you have like 3 choices and they give you 3 attempts, then you will be bound to find the right answer. Okay, so let's look at the UDP protocol, which is one of the 2 protocols at the transport layer. So UDP is really a bare bones protocol. It is provides no guarantee. It's a best effort service, which means when you use UDP, your segments or packets, if you wish, can be lost, can be delivered out of order. But the upside of UDP is that it is connectionless, meaning you don't need to do handshaking to set up any kind of connection before you can send data. And also another thing with UDP is that each packet or segment is handled independently of the other segments. So you may ask, so if it is bare bones and provides no guarantee, why even bother, right? Why should we use UDP? And I think I already gave you some answers last time or the time before that. And that is, here I'm going to give you some examples of use of UDP. Oops, what happened here? So there are some applications such as streaming multimedia applications, which can tolerate data loss. And if your application can tolerate data loss, then you don't need the reliability aspect of TCP, right? So that may be a reason why you want to use UDP. Now, another case of application where you may want to use UDP is if you just have a simple short query response transaction, right? Just send a short query, get a short response. So you don't, you may not want to go through the cost of the overhead of setting up a TCP connection just to send a short message and get another short reply back. Okay. A good example is the DNS application, which stands for Domain Name System. Domain Name System. So Domain Name System is the application that allows you as a user to type a logical name such as google.com. Okay, so when you want to get to a website, you and I type a logical name. We do not type the IP address of the website. However, in order to reach the website, we need to tell the network what is the IP address, because the network does not understand the logical name actually, right? So when we type google.com, what happens is that our machine will send a query to a DNS server to ask the DNS server, give me the IP address of google.com. So it's a short query, right? A short message, just google.com, what is the address of google.com? And then the reply comes back. It's also a short reply, just an IP address, essentially. And then we're done. So this is a good example where we want to use, where it may be a good idea to use UDP. You don't want to incur the cost of TCP, or complexity of TCP. Okay, SNMP is another example. So this stands for Simple Network Management Protocol. Okay, this protocol is used by the network operators. So when you have a network, you operate a network. So you have all these equipments, right? The routers, the links, and so on, which are all over the place, right? All over your network. And what you want ideally is to minimize the cost of the maintenance. So maintenance, that can happen, for example, when the equipment goes down, right? When the equipment goes down, or when the equipment is about to go down. So preferably you want to be able to know that ahead of time so that you can send the maintenance crew to fix the equipment. Now, how can they know? How can the network operator know? They do not have a kind of staff sitting next to each piece of equipment in the network. So instead, they will have some centralized location where they can interrogate the equipment, right? Interrogate to know what is the health status of the equipment, and in order to get the health status of the equipment, they will use the SNMP protocol. Okay, so the SNMP protocol can be used to know, okay, what is the how well the equipment is operating. Is it dead or is it sick, or that type of information. Okay, now another thing to also keep in mind is that when we use UDP, UDP does not provide reliable data transfer, but that does not prevent us from having reliable transfer if we want reliable transfer, because we can implement reliability at the application layer, right? So typically, to have reliability, we just retransmit if the data is lost. Okay, so that can very well be implemented at the application layer, and in that case, we don't need TCP because the TCP reliability will be redundant. And if we do the reliability at the application layer, then we can better tailor the mechanism to our needs, to the needs of the application. If we use TCP, it's some kind of one-size-fits-all mechanism, right, which provides reliability. So it may not necessarily be the best choice. Okay, so now a quick question. What are the two main functions that UDP add to IP? So given that UDP does not give us any guarantee, it does not give data loss guarantee, may deliver out of order, then why would we want to use UDP? So there are essentially two main functions that UDP does provide. The first one, we have seen it already. It's the multiplexing, demultiplexing, right? Remember, when you use UDP socket, then there's that destination port number, right? If you use UDP, in the header of UDP, there's the source port number and destination port number. And these port numbers, they are used at the destination to deliver to the proper UDP socket. Okay, so that is one function, main function of UDP, multiplexing, demultiplexing. The second function and that one we haven't learned about yet, is to be able to detect error detection. Okay, so when I say error, I mean bit error. Okay, so now we can look at the header when you use UDP. So if I use UDP protocol, then this is going to be my header. It's a very simple header. Okay, it's just 64 bits. So it starts with the source port number, destination port number. So these port numbers, they are common to UDP and TCP. And then you have the length of the whole segment. And you have that field called the checksum. Okay, this is how a UDP segment would look like. And then you have the payload, which is where the application data is. Now, another reason why you may want to use it UDP is, is that it's simple, right? You don't need to set up a connection. The header is small, and you do not have congestion control. So if there's no congestion control, the application can blast data as fast as it wants. The sender is not throttled by anything. Okay, so it may be a plus, it may be a minus. But again, it depends on your needs and what you want to do. Okay, now let's look at the checksum. So the goal of the checksum is to allow us to detect errors. Okay, the errors is a bit, here we mean bit error, right? Something that was sent as a 1, received as a 0, or vice versa. So how is that done? At the sender side, the sender will calculate the checksum, the UDP checksum. How does the sender calculate the UDP checksum? It will look at the whole segment, including the header, and it will treat this segment as a sequence of 16-bit integers, because the segment is a bunch of bits, right? So I can split that bunch of bits into chunks of 16 bits. Each 16-bit is read like an integer, 16-bit integer. And then I just perform an addition of these 16-bit integers. But the addition will be using one complement sum, so which is a specific type of arithmetic, but conceptually it's an addition. And then the sender will put the result of the addition into that field called checksum. Okay. Okay, no more. Is it parity bit? No, because the checksum is not a single bit. The checksum is 16 bits. The parity bit is only 1 bit. But it is the same purpose, right? The parity bit is to detect error. The checksum is also used to detect error. But when you use a checksum, you have, in the case of UDP, 16 bits of checksum. Now, the checksum is optional, meaning that the sender is not required to calculate a checksum. So if the sender decides not to calculate a checksum, it needs to tell the receiver, right, that I did not calculate a checksum. So by convention in UDP, if the sender does not calculate the checksum, it will just put zeros in the checksum field. And then at the receiver will do the same computation, right? The addition of the 16-bit integers. And then it just compare the result of its calculation with the checksum that it receives from the sender. And if they match, then we just consider that there has been no error. If they do not match, then there is an error. But we just know that there's an error. We don't know exactly where is the error, right? Okay, so now we have an interesting question, because what happens if the sender decides to calculate the checksum, but the result of the calculation happens to be zeros, all zeros? The sender cannot send all zeros, because all zeros means no checksum. So we need a way to differentiate, right, the case of no checksum from the case where the checksum is all zeros. So we get back to that shortly. But let's look in more detail at the checksum algorithm. So we break the data into 16-bit integers, add them together. So now this is the one complement arithmetic. How it works is that to represent a number of an integer n, you just revert all the bits of n. For example, if n is 7, in binary, it is 0, 1, 1, 1, right? This is 7. To represent -7, we just flip all the bits one by one. Okay, so 1, 0, 0, 0 means -7. That is how one complement arithmetic works. Okay, so now because of that, okay, I will get back to that, right? So this is the one complement arithmetic, the way it works. And then you add all the 16-bit integers. And if there's a carryover, you add the 1 to the result. And then finally, you take the one complement of the result. That is, you revert all the bits again to get the final result, which is the checksum. Let's look at an example. Okay, this is a very simple example where the message is 32 bits. So these are my 32 bits. They are split into two 16-bit integers. I do the addition of the two 16-bit integer. I get this value. Now there's a carryover. So I'm going to take this carryover, add back to the result. And this is what I get after I add back the carryover. Okay, this is what I get. And as the final step, I flip all the bits. And this is going to be my checksum. Okay, so now let's get back to my earlier question. How can we differentiate the case where the sender does not want to calculate the checksum from the case where the checksum is all zeros? The idea here? Okay, so it's going to be based on the one complement arithmetic. So if the sender decides to calculate the checksum, but the result is all zeros, remember, 0, if we represent in binary, will be all zeros, right? All zeros, that is 0, that means 0. But minus 0 is also 0. Minus 0 is also 0. So minus 0 is represented by all ones. Okay, you flip all the bits, you get -0. It also means 0. So if the sender decides not to calculate the checksum, you just send zeros in the checksum. If the sender decides to calculate the checksum, but the result happens to be 0, it will send all ones. Essentially, it will send -0. And that is how you can differentiate the two cases. Any question? Okay, as usual, I give you the pointers. All right, so let's move on to the next, which is Unit 8. Okay, in this unit, we are going to learn about the mechanism that can be used to provide reliability, right? Okay, so given that we have underlying network which is unreliable, what mechanism can we add on top to make it reliable? So that will be referred to in this class as reliable data transfer, or RDT. So this is the problem. This is a segment of the problem. We have the application layer. Where we have the sending process and the receiver process, right? And we want to provide a reliable service, a reliable delivery service to the application layer. So that's seen from the application layer. It looks like the communication channel is reliable. But in reality, we know that the underlying network is unreliable, right? In particular, because the buffer may get full and the packet may have to be discarded, right? So under the hood, actually it's unreliable. So we need to insert something which is called reliable data transfer protocol between the unreliable underlying network and the service that is provided to the application layer. So the more unreliable the channel is, the more problem the channel has, the more complex we will need to have the more complexity we have in the reliable data transfer protocol. Okay, so here we're going to have some protocol, and it takes. So here, let's define some terminology. We have a sending side, we have the receiving side, and the sending side will receive data from the application. And the primitive is called RDT send data. So because it provides a service which makes a channel look reliable, the data that is received here will be delivered reliably to the application at the receiver, right? But if we go deeper under the hood, actually the reliable data transfer, we will need to use the service of unreliable channel to send the data as a packet. And when it wants to send the data as a packet, it will use this primitive, which is called UDT send. So here it's RDT, R for reliable, and here U for unreliable. So when it uses UDT send to send the packet, we know that this packet may be lost, or it may be delivered out of order. Okay, because here we have an unreliable channel. And then the receiver, at the receiver side, we have another primitive, which is RDT RCV. Okay, so to get whatever packet gets received will be delivered to this reliable data transfer protocol, and these two sending side and receiving side, they will do what is necessary so that this whole thing will look like a reliable channel. And the delivered data will be the primitive that is used to deliver the data to the application. Okay, so that is a kind of terminology. Okay, I already went through this. So in order to better understand the reliable data transfer issues, we are going to do that incrementally, stepwise, right? So which means is that we will start with a very simple case of unreliable channel, and then we make it really more and more realistic and more complex. And then we see how we need to correspondingly enhance our reliable data transfer protocol. Okay, and then in this analysis, we can consider only unidirectional data transfer, meaning that we will consider a sender and a receiver. However, this does not limit the general applicability, because if you have a bidirectional if you need bidirectional data, reliable data transfer, you just implement the sender and the receiver, right, at both endpoints. So you have the data flowing in both directions. But even though it's a unidirectional data transfer, we will see shortly that we still need some a channel going in the reverse direction for control information. Okay, so we need that to be able to do reliable data transfer. Essentially, we need a feedback channel. And then we'll use finite state machines to specify the sender and the receiver. So finite state machines, I think that you're all familiar with that. That is typically used to specify communication protocols. Okay, so just to refresh our memory, in a finite machine, we will have state, and then we have transition from one state to another, which are shown by arrows. And attached to each transition, we can have the event that causes a transition, so that we'll put that at the top. And at the bottom, we have the action, possible action that are taken when we transition, when we do the transition. Okay, so event actions. That's what we're going to use in the description of reliable data transfer. Okay, so let's start with RDT 1.0. By the way, RDT is not an actual protocol. It's not a real protocol. It's really a kind of a conceptual tool that we use that I use to teach you the concepts of the RDT, or reliable data transfer, right? So there's no such thing as RDT protocol on the internet. However, the concepts that we learn here with RDT, we will see next how they are applied, how they are used in the case of an actual protocol on the internet, which is TCP. Okay, so let's start with the simplest case, which is actually the underlying channel is reliable, perfectly reliable. So not realistic, right? But let's just start with that. So it's perfectly reliable, which means there's no bit error, no loss of packets. So in that case, how would the RDT look like? So it will be RDT 1.0. At the sender side, the FSM has only one state. This is a state where it will wait for data. So call here just means data to be transmitted, right? So wait for data to be transmitted from above, which is the application layer. So when there's data to be transmitted, RDT send data. This is the triggering event. The action it takes is simply to build the packet, right? Make packet, put the data into the packet, and then just send the packet over the underlying channel, which in this case is assumed to be perfectly reliable. So since we assume it's perfectly reliable, there's no need to do anything else, right? Because we know that this packet that is sent will be received reliably at the destination. Essentially here, RDT 1.0 does not have to do anything. Just put the data into a packet and send it. And then at the receiver, there's only one state for the FSM. That state is to wait for the reception of some packet. Wait or call from below, coming from the layer below. Okay, so if the event is a reception of a packet, then simply it will extract the data from the packet and then deliver that data to the layer above, which is the application layer. Okay, very simple, but unrealistic. Okay, now let's make our underlying channel a bit more realistic. So now we are going to assume that the underlying channel may flip the bits. Okay, so we may have bit errors in the packets. And here we need to make an assumption that we have a means to detect the bit errors. There must be some way to detect, right? If you cannot detect bit errors, there's nothing you can do. So for example, we assume that it uses a checksum, like the UDP checksum, right, to detect bit error. Okay, so now the question is, once bit errors have been detected, how do we recover? Okay, so question, so we look at the human case. How do we recover from errors during conversation? So first, what is an error during, let's say, a phone conversation? And then how do we recover from errors? Yeah, repeat, right? But what is an error? An error is, for example, there was some noise, right? The person was speaking, but there was some noise. You cannot hear very well. So you have detected an error, right? You know that you were not able to hear. You detected the error. And then the other person will repeat, but how does the other person know that they should repeat? Yes, exactly. The receiver asks the speaker to say that again. So we're going to do the same thing here, right? We're going to do the same thing here. So the receiver detects that there's an error. The receiver now will use the feedback channel to ask the sender to retransmit. Okay, how does a receiver give the feedback to the sender? So there will be essentially two types of feedback. One is called acknowledgements, or ACKs, and the ACK simply tells the sender that the data was received without error, right? The packet has been received okay. A negative ACK, or NAC, means that the packet will receive, but it had some errors in it. So this is sent over the feedback channel back to the sender, and then the sender just retransmit the packet if it receives a NAC. Okay, so that is how we recover from errors. So in order to do that, we need some new mechanism. We need to add some new mechanism to RDT 1.0, and the result is called RDT 2.0. Okay, so we need error detection at the receiver, for example, checksum, but there are other error detection mechanisms. And then we need to have a feedback channel where we can send these control messages, which can be ACK or NAC. Okay, and then if we look at the FSM for 2.0, at the sender, we have two states. This is the initial state where the sender waits for data to be transmitted. If there's data to be transmitted, it will build the packet. So this is like before. It will send the packet over the unreliable channel. But now the new thing here is that it will transition to another state where it will wait for the feedback from the receiver, right? So it will wait for ACK or a NAC. And in that state, two things can happen. It can receive either a NAC or a positive ACK. So if it receives a negative ACK, this is the event, right? It receives a feedback, a packet, and it is a negative ACK, then it will retransmit. So it will UDT send the same packet, this packet, right? What should be here. It will retransmit that same packet. The other type of event is that it receives a feedback and it is a positive act. In that case, the sender knows that the transmission of the packet is successful. It does not need to do anything else. So this simply means empty, right? No action. And it just transitions back to the other state where it's going to wait for new data from the application layer. Okay, so you see, pretty simple. Every time there's data to send, then wait for the feedback, and then depending on the feedback, retransmit or not retransmit. Now, note here that in this state, this can happen multiple times, right? So it may receive a negative act, retransmit, but the retransmission can also have bit errors, and then there will be another negative act again, right? So it will stay in this state as long as there is no positive act. So it will stay in this state. If there's a negative act, it will transmit. If there's a second negative act, it will retransmit again, as many times as needed until there's a positive act. Okay, and then at the receiver, this is the FSM. So essentially, there are two cases. If the error is detected or no error is detected, right? So if the error is detected, which is this case, receive a packet and corrupt, meaning an error is detected, then send a negative act, and then wait again, right, for the retransmitted packet. Now, if the data is received and it is not corrupted, meaning no error is detected, then it will extract the data from the packet, deliver the data to the application layer, and then sends a positive. Okay, so now if we look at an animation, how it operates when there are no errors. So it starts from this state. Okay, these two states, the two initial states, and now there's data to be sent. Here we assume that the data is received and no error is detected. So we're in this case. The receiver sends back the positive act, and that will make the sender transition back to this state. This is the case where there is an error. Okay, it sends, but the packet is corrupted. So the receiver sends back a negative act. And this will create this event at the sender. The sender will retransmit. And here I assume that the retransmission is okay. Now the receiver sends a positive act and the sender transition back to this state. Okay, now too good to be true. No free lunch in life. RDT 2.0 has a fatal flaw. The problem here is the feedback, which is positive act or negative act, can also be corrupted. Okay, because we have bit errors in the channel. So if the sender receives something that is corrupted, then the sender does not know if it is a positive act or negative act, right? There is some feedback, but now I don't know whether it's positive or negative. So to be safe, the sender should retransmit anyway, right? So if it is corrupted feedback, the sender should retransmit. But that retransmission can lead to duplicate packets because the first packet was not corrupted, right? The receiver sends back a positive act. The positive act was corrupted. The sender retransmit. So now we have duplication of data. And remember, for reliable transfer, we we cannot have duplication, right? The data should be delivered without duplication. So we need to be able to handle duplicates. To detect duplication, we will just add a sequence number to each packet. Okay, so that, let's say we start with packet sequence number 1, right? Packet number 1. So when you retransmit the packet, it will carry the same number. It will still be packet number 1. So the receiver can look at the number to determine that whether it's a duplicate or not. Okay, so this kind of behavior that we have seen with RDT is called stop and wait, right? The sender sends one packet, and then it will wait for the receiver response, whether it's a positive ACK or a NACK, right? But it waits. It's not going to send new data. It will wait as long as needed. So it's called stop and wait protocol. Okay, now if we want to handle the corrupted feedback with a sequence number, then the finite state machine at the sender will look like this. Essentially, we duplicate the states because we have an additional state variable or state information, which is the sequence number of the packet that we are going to send. Okay. So in the simplest case, we can just use 1 bit for the sequence number. So we may start, for example, with the first packet is 0, next packet is a 1, the third packet is a 0, the fourth packet is a 1, and so on. Okay, essentially it's a counter, right? It's a counter, but it's a 1-bit counter. So it will be 0, 1, 0, 1, and so on. Okay, so if we compare with the previous case, 2.0, essentially we have that additional state information, which is the sequence number that we're going to use next. And here we factor in that sequence number in the states of the FSM. So all the states which have a 0, in all the states which have a 0, the sender is dealing with sequence number 0, with packet sequence number 0. In the state which have a 1, it is sequence number 1. Otherwise, the rest is the same. Okay, so this 1 is the mirror image of this one. The only difference is here the sequence number is 1, here's the sequence number 0, and this one is the same. It's a mirror image. Okay, so let's just walk through some simple case. So initially we start here. This is the initialization. Okay, there's data to be sent. The sender will build the packet, make packet. So here you see we added the sequence number. Here sequence number 0, right? 0, because state 0. This is the data, and we protect it with a checksum. Send the packet. Like before, we go into a state where we wait for the feedback. Okay. So here in this state, there are 2 possible cases, right? So one case is we receive feedback and it is corrupted or it is a negative ACK. In both cases, we're going to retransmit, right? So corrupted or negative ACK, we retransmit. And then we stay in this state. We stay in this state as long as we do not receive a feedback that is not corrupted and a positive ACK. Okay, so corrupted, retransmit, negative ACK, retransmit as many times as needed until we receive the this one. And when we receive this one, then we are done with this packet, the packet sequence number 0. Now we are going to wait for new data from the application layer. But remember, because new data is a new new packet. So the sequence number should be incremented. Now the sequence number is the 1. And that's why we were in this state, 1, not 0, but 1. And here the logic is the same, right? Send data, wait for the feedback. And if we're done, if we receive a positive feedback, we go back to sequence number 0. Any question here on the logic of the sender, FSM, for 2.1? Okay, now let's look at the receiver. So this is initialization. So we start with sequence number 0. And then there are different cases here. So let's look at the case where the receiver receives something that everything is okay, right? So it receives a packet, it is not corrupted, and it has the right sequence number 0, because here we know that normally we start with number 0, right? So everything is in sync, no error. Extract the data, deliver it to the layer above, build the positive ACK. But now the ACK needs to carry a checksum because the sender must be able to detect if the feedback is corrupted. So we need to attach the checksum to protect the ACK. Okay, and then send the ACK. Send the ACK. UDT send packet. The packet has been built. So here, as far as the receiver is concerned, it is done with the packet sequence number 0. It's done. So it's now to transition to a state where it expects to receive next a packet with sequence number 1, packet number 1, right? So in this state, let's look at the case where everything is fine again. So this is the mirror image. So it expects to receive packet number 1. It does receive packet number 1. It's not corrupted. It does the same thing, goes back to 0. So the next packet is 0. So it's going to, normally in the case where there's no error, no corruption, nothing, everything is fine, then the receiver just transition between these two states, right? Receive 0, now next, send a positive ACK, next wait for 1, send positive ACK, and so on. Okay, let's look at the error cases. So let's say it wait for 1 from, it has sent back the positive ACK, but now it's received something that is corrupted. So it needs to send a negative ACK, which is what it does here. But it may also receive something that is not corrupted, but it has the wrong sequence number. Okay, sequence number 0, but it waits for sequence number 1. So why do you think that may happen? Why do you think that the receiver sends back a positive ACK for this one, sequence number 0, but then after that, why does it receive again packet number 0? It did receive it here, but it received again here, sequence number 0. How can that happen? So essentially, there's a loss of synchronization. Yes, duplicate, correct, but why do we have a duplicate? Because that's how it detects duplicate, right? This is a duplicate, but why do we have a duplicate? Why do we receive a duplicate? What caused the reception of a duplicate? So if the receiver receives a duplicate, that means the sender did retransmit, right? The sender retransmitted packet 0. So why did the sender retransmit packet 0? In what case does the sender retransmit? In what case does sender retransmit packet 0? Yeah, not getting ACK, but can you be more specific? What do you mean by not getting an ACK? So you look at this FSM, the sender transmitted packet 0, and then after that, in what case does it retransmit? Does it retransmit this packet 0? Where on this FSM does the sender retransmit packet 0? Here. It's the same packet. And it retransmit packet 0 if it is a negative ACK or, yes, exactly, or it's corrupted, right? So it may happen. It may happen that the sender retransmit packet 0. And it happened because this may happen because the this ACK was corrupted. This ACK was corrupted, so the sender, to be safe, retransmitted. Okay, so even though the receiver has received packet 0, but the sender retransmitted. So this is a case of duplicate. And what the receiver does is that it's not going to extract the data and deliver, because that would be a duplication, right? It should filter out a duplicate, but it needs to send a positive ACK to the sender. Otherwise, the sender does not know, right? So it need to tell the sender, I have received it, so do not retransmit. Okay, that's what happens here. Okay, and then the other case is it receives, it waits for packet 1. It does receive packet 1. It's not corrupted. Everything is fine. So they extract the data. It will build a positive ACK, send the positive ACK, and now next it will go back to waiting for packet number 0. Okay. Any other question on this FSN for 2.1? How the receiver determine that he has received the correct? What do you mean by correct one? You mean error-free, or what do you mean? What do you mean by correct? Well, it uses the error detection, right? That's an error detection scheme. For example, checksum. That can be used by the receiver to know if there's a bit errors. Okay, quick discussion on 2.1. So with 2.1, because we want to be able to detect duplicates, we need to add a sequence number to the packet, right? And it turns out that we only need 1 bit for the sequence number. So with 1 bit, we'll have 2 values, 0 and 1. And it turns out that 1 bit is enough. So I will probably post some discussion on Piazza, why it's enough, why we don't need more than 1 bit. And the sender must check that the feedback is not corrupted, right? This is the requirement. And if we compare with 2.0, we see that we have double the number of states because we need to remember the next sequence number, okay, in the state. So we have twice as many states. Receiver must do the duplicate detection using the sequence number. And in order to do that detection, the expected next sequence number is captured in the state of the FSM, right? The state indicates whether 0, 1 is the expected sequence number. And this is a note that the receiver cannot know if the feedback was received correctly at the sender. It may be corrupted, right? Okay, now actually I'm going to skip the 2.2. I don't think it's that important. So let's skip to the 2 and go straight to 3.0. So now we're going to make the channel even more realistic. And in addition to bit errors and the corruption of the feedback, you can have data loss. Okay, so we know data loss happens, so we need to be able to handle data loss. So with everything we have defined, the checksum, sequence number, the ACK, retransmission, and so on, that will not be enough because the ACK is lost, could be lost, right? So the positive ACK may be lost. And if the ACK is lost, the sender will wait forever. Will stay stuck in that state where it waits for positive ACK. And then the positive ACK never comes. So there's a problem. So the approach here is that we're going to use a timer so that the sender will not wait forever in that state. Right? It will just wait for a reasonable amount of time for the ACK. And if the timer expires and it still has not received an ACK, it will retransmit. Essentially, if the timer expires, the sender considers that the ACK has been lost. Okay, so it will retransmit. The ACK has been lost or the packet. Okay, either the packet has been lost or the ACK has been lost. So in any case, to be safe, retransmit. Now the retransmission may be a duplicate because the ACK, because it could be that the packet was not lost, right? So packet 0 was received. The receiver sends back the ACK is lost. So the sender times out, retransmit packet 0. So this will be a duplicate. But we can handle duplicate because we have the sequence number. Okay, so we are able to handle the duplicates. But the requirement here is that now the receiver must specify when it sends back the ACK, it must specify the sequence number of the packet that is being ACKed. Okay, so it must say ACK of packet 0 or ACK of packet 1. Okay, so essentially here we need to add a timer at the sender side for the countdown. Would be a countdown. Okay, so here I just highlight. So visually you can see that the FSM at the sender also has 4 states. If we compare with 2.1, okay, we have the wait for call 0, wait for ACK 0. Essentially it's the same, but we have a few additions due to the timer because we have to add a timer. And I'm going to highlight the timer additions. First, we have one here. So when we send the packet, start the timer. Okay, so this part is the same as 2.1. This is an addition. Okay, start the timer. And then go wait for the ACK. So this part is the same, but here we have an addition. We have an additional event, which is timeout of this timer. So when it times out, retransmit. UDT send packet. This same packet. So this is a retransmission. And start the timer again because there's no guarantee that this retransmission will be successful. So we may have to retransmit upon timeout multiple times. Okay, so start timer again. And then it could be that we time out again, right? So we may need to do this multiple times. Retransmit, timeout, retransmit, and so on. Now, if we receive a positive ACK, which is the case here, then we can stop the timer because we know that it has been successful. So we don't need to run the timer, stop the timer. And then this part is the mirror image of this. So we also have the start timer, timeout, and then stop time. Okay, essentially that is the addition, which is the timer. Okay, so let's look at a few cases of RDT 3.0 in action. Let's first look at the case where there's no loss. Everything is fine, okay? So the sender sends packet 0 to the receiver. The receiver sends ACK of 0, ACK of packet 0. The sender receives ACK of 0. Now it increments the counter. Okay, go to the other state, which is sequence number 1. So it sends packet 1, gets received, ACK of 1, increment the counter. So now it's back to 0 because it's a 1-bit counter. Okay, so 0, ACK of 0, packet 1, ACK of 1, packet 0, ACK of 0. Okay, simple. Now let's look at the case of packet loss. So packet 0, ACK of 0. Okay, we are done with this packet. Next, the sender sends packet 1. Packet 1 is lost. So because it's lost, the receiver does not send the ACK, right? The sender does not receive the ACK, but the sender had a timer waiting for the ACK. So when the timer times out, it will resend the packet 1. And then from that point on, we are back in business, right? You send packet 1, ACK of 1, packet 0, ACK of 0. Now let's look at the case where the ACK is lost. Okay, so here we start the same. Packet 1 is not lost. Receiver receives packet 1, send ACK of packet 1, but the ACK itself is lost. So the sender will time out and will resend packet 1. But now this is a duplicate, right? Because packet 1, packet 1. And the receiver can detect duplicate because it carries the same sequence number. But regardless, the receiver will send ACK of 1. Essentially, it needs to tell the sender, I have received packet 1. Do not retransmit it anymore, right? I have received it. So it's an ACK of 1. And then from there on, the sender increments the counter, right? Send packet 0, ACK of 0. Okay, now let's look at a different case, which is a premature timeout. Essentially, the ACK is not lost, but the ACK took too long to get to the sender. And in the meantime, the sender has timeout. Okay, this is what we have here. 0, packet 0, ACK of 0. Packet 1, ACK of 1, but this ACK is somehow delayed or the timer was too short, whatever, right? So it times out. It will resend packet 1. So the receiver, this is again a case of duplicate, so it can detect duplicate. But now, because we have the ACK of 1, which is eventually received at the sender will transition to the other state in the FSM. And now it can send packet 0, right? Send packet 0. Now, this thing is, because it received packet 1, so the logic of the receiver is that it will receive packet 1, it should send ACK of 1. So it sends the ACK of 1. But here, the sender sends packet 0, right? So it expects to receive ACK of 0. And it may receive ACK of 1, but because this is not ACK of 0, it will just do nothing. It just ignore it because this is kind of no new information because it already received ACK of 1 here. This is just a repeat. It's going to ignore it, do nothing. And it will actually wait for ACK of 0, which eventually comes here. Okay, so if you go back to the FSM, you can see that when it is in the state where it waits for ACK of 0. If it receives ACK of 1, it would do nothing, okay, which is the case. All right, that concludes this unit. Okay, I think there's a question for me. How this mechanical bypass is possible traffic congestion in the case that a delay causes a delayed ACK? No, there's nothing you can do. If traffic is congested, your packets as well as the ACK or NACK will be delayed. Does that answer your question? So actually, that's what we have here, right? This is a delayed ACK. This is a delayed ACK because the traffic was congested. So we delay the ACK and then we time out. But what this shows us is that even though you may have variable delay, premature timeout, all these kinds of things, RT 3.0 will work. It will work correctly. Okay, correctly meaning that there will be no duplicate at the receiver, right? There will be no loss because the sender will retransmit as many times as needed. Okay, so in that sense, RTT 3.0 is correct. Give you reliable data transfer when you have bit errors, when you have packet loss, and when the feedback may be corrupted. Any other question? Okay, if not, then to which part of the packet delay calculation does RDT apply? Okay, everything. Okay, packet delay calculation. So this ACK is a packet. All of these are packets, right? So even though I didn't call it packet, but it is a packet. The ACK is carried in the packet. It is a packet. So like any packet, the total delay will be the sum of these four components of the delay that we have learned. So we have processing delay, transmission delay, propagation delay, queuing delay. Does that answer your question, James? Okay, any other question? Okay, so thank you for your participation. I will see you next week and have a good weekend.